Hi, everybody. Welcome back. We're going to continue our discussion on confidence intervals and introduce a new distribution called the t-distribution. First, we're going to talk a little bit about the t-distribution. The man behind the t-distribution is a statistician named William Seeley Gossett. He was an English statistician who worked for the Guinness Brewery in Dublin, Ireland. Guinness was a company deeply invested in quality control and optimization. They wanted to ensure consistent product quality while minimizing costs in experiments, for example, testing barley yields and brewing techniques. The problem is that they only had small samples to work with. Statistical tools, if you remember from our previous few lectures on sampling distributions, sampling distributions were normally distributed only if our sample size was large enough, especially if we're working with a population where the shape was unknown or the shape was just not normal. We needed to have a large sample in order to assume the sampling distribution was normal. And the statistical approach using normal CDF and using the math that's behind normal CDF was what most statisticians relied on. So there was no ability to do any kind of analysis on data that came from small samples. Gossett needed a method for making inferences, making our statistical inferences, estimating means, testing hypotheses, when only small samples were available. For example, he might test barley from just a few fields rather than a large data set. So, Gossett developed the t-distribution. This was in 1908, so it's not very long ago. And the t-distribution accounts for the additional variability that's introduced by small sample sizes. Remember going back to our Desmos data visualization. When n was 10, when we sampled size 10, we had more variability than when n was 80. So we do have a lot of variability when we use small samples. So in order to account for that variability, this new distribution adjusts for that uncertainty, and we don't have access to a standard deviation from the population, sigma. We have access to the sample standard deviation from the sample. So the standard deviation is unknown in the kinds of work we're going to do today, but the sample standard deviation will be provided. So here's a look, and you can use this link if you have access to this PowerPoint, you can just click this link and go to Desmos. This is an example of what the normal distribution looks like compared to the t-distribution. The t-distribution is also a bell-shaped curve, but mathematically it's slightly different than the normal distribution, especially when you get down. I shouldn't have drawn on there with red. Let me get rid of the red. When you get down towards the left, you see how the red line, which is the normal distribution line, tends to go to the horizontal axis faster, and the blue line kind of sits above it. So that makes the t-distribution, you can think of them as having heavier tails. The tail on the left and the right, you could see that the t-distribution is a little bit higher in both those areas. So this gives us a greater chance of extreme values with smaller samples. So extreme values with the normal distribution are not as likely, but you could see we do have this additional heavier tail that allows for more extreme values with the t-distribution. We use the t-distribution when we're working with small samples and when the population standard deviation is unknown. It adjusts for the greater uncertainty, making it a critical tool for accurate statistical inference. Gossett's work highlights the practical origins of statistical methods and their real-world applications. We will use the t-distribution and t-scores instead of z-scores t-scores instead of z-scores for confidence intervals when we do not have the population standard deviation. So remember that we had 3 levels of confidence in the previous lecture, 90, 95, and 99. We are also going to have 3 levels of confidence when doing confidence intervals for the t-distribution. In the same way that z-scores are associated with the normal distribution, t-scores are values that correspond to the t-distribution, and they're used in statistical inference when working with small samples or when the population standard deviation is unknown. So do you see in each of these pictures, you see t sub 95, t with a subscript 95% on the right border of the shaded area, T with a subscript 97.5% on the right border, and T with a subscript 99.5% on the right border. What do you think those refer to? So if you imagine that the 90% of the area in the center is blocked off, then 5% is left on the far left and 5% is left on the far right. This 95% represents the area to the left of this this border, this right border on the shaded area. 95% of area is to the left. And if we do the same thing with 95% in the middle and recognize that that leaves 2.5% on the left and 2.5% on the right, this 97.5 represents the sum of 95 and 2.5. It's the entire amount of area going down to negative infinity to the left of 97 of this vertical line here. And with 99% in the center, there's 0.5% on the left, 0.5% on the right, and 99.5% here represents 99.5% of area to the left of this vertical line. They are the areas to the left of the t-scores when the middle 90, 95, and 99% of areas are blocked off. We are going to be needing these for our confidence interval formulas. It's slightly different than working with z-scores. So there is a difference here, and you'll see that you'll get different answers than if you were to work with z-scores. Confidence interval formulas for the t-distribution. When creating a confidence interval, when you don't know the population standard deviation, you're going to use the sample standard deviation in its place. And instead of z-scores, you are going to be using t-scores. And the formulas are very similar to the previous lecture. For a 90% confidence interval, we take the x-bar, and then instead of subtracting a z-score, we're going to subtract a t-score. And instead of multiplying by the standard deviation divided by the square root of n, we're going to multiply by s divided by the square root of n, because the population standard deviation won't be provided to you. It will be unknown. Okay, so you're using the sample standard deviation in its place. And then on the right, the same thing, x bar plus t 95% times s divided by the square root of n. Now, we haven't yet looked at what t 95% actually is. It turns out we're going to need our calculator for this part to figure out what the t-score is. It changes based on the sample size. So unlike z-scores that they were the same, it was negative 1.645, positive 1.645, and then negative 1.96, and positive 1.96, negative 2.5, I can't remember, 7.5. I can't remember. I'm sorry. You should always have these on a piece of paper. Nobody's expecting you to remember that. And the positive version, 2.5, whatever it was. These z-scores are unchanging. They stay the same no matter what confidence interval you're creating when you're doing it with z-scores and when you have the population standard deviation. But when you don't, and when you're using t-scores, these t-scores are not anything that you could memorize. They're not a set like these are. And I'll show you how to find them in a minute. So with a 95% confidence interval, we're using 97.5% and 97.5%. And for a 99% confidence interval, 99.5% and 99.5%. And let's recall where that all came from. It was this previous picture here. Okay, for a 90% confidence interval, 95% of area lies to the left of the vertical cutoff, 95.95%. For a 95 confidence interval, the area to the left of the vertical cutoff is 97.5. And for a 99% confidence interval, the area to the left is 99.5. The t-scores for that we're going to be using vary due to the size of the sample. They can't be memorized like the 3 z-scores. There's a function on the calculator that we are going to be using to find those t-scores. It's called inverse t, and it determines which t-score to use for each confidence interval formula we will be working on. Let's work on our first problem, blood glucose levels in patients. A random sample of 16 patients with type 2 diabetes was selected from a local clinic to estimate the average fasting blood glucose level of patients at the clinic. The sample mean fasting blood glucose level was found to be 125, with a sample standard deviation of 15. Now, because we don't have the population standard deviation, we cannot calculate the standard error. We're going to be using the sample standard deviation instead, and we're going to be using the t-distribution in this problem. So the key thing to look for is whether or not you are provided with S or sigma. If you are provided with sigma, most likely you're using the standard error and you're using the normal distribution. And if you're provided with S, most likely you're using the t-distribution. Now, I say most likely because outside of this class, you may be dealing with problems that give you different sample sizes. In this class, I'm going to always assume that if you have the S, then you'll be using the t-distribution regardless of the sample size. And if you are given sigma, you're going to be using the normal distribution, and I will assign a sample size that makes the sampling distribution normal. So what we're going to do in this problem is construct and interpret a 95% confidence interval to estimate the true mean fasting blood glucose level of all patients. We are trying to estimate mu given the X bar 125. We're going to find the margin of error, and we are going to repeat this process for a 99% confidence interval. Now again, we're using the t-distribution because we are not provided with sigma, we are provided with S. Given that the sample size is 16, the X bar provided is 125, and the sample standard deviation is 15, we have a confidence level of 95%, which puts us with a t-score, remember this picture, a t-score where the subscript is 97.5. Now that comes from looking at the middle as 95% and each tail containing the remaining 5%, so 2.5 on the left, 2.5 on the right. So the area in total to the left of this vertical cutoff is 97.5%. As an area on the calculator, we're going to be entering that as 0.975. So this t-score has got to be converted to a notation, like we see here, into an actual number that could be plugged into a formula. So putting that t-score here and here, we need to find out what that t-score is. The rest of the formula looks very similar to what the confidence intervals looked like in the previous lecture. X bar minus a t or a z-score multiplied by a standard deviation divided by the square root of n. And on the other side, we add x bar plus the z or t-score times the standard deviation divided by the square root of n. So to find out what that t-score is, we are not going to commit this to memory because there's just too many t-scores to remember. With the z-scores, we only had to know 3 of them, and they were for the 90, 95, and 99 level, confidence levels. But for t-scores, there's a whole lot of values, a whole lot of t-scores that are the result of different sample sizes. Different sample sizes are going to give different t-scores even for the same confidence level. So for this confidence level, 95%, we're going to go to our calculator, inverse t, and for area, we're going to plug in 0.975, but we're also asked about something called degrees of freedom. Degrees of freedom is a number that is going to be 1 less than your sample size. And since your sample size here is 16, this time we're going to use a degrees of freedom of 15. So let me go to the calculator and show you what this looks like. You're going to go to the same location for the same place as we went for normal CDF and inverse norm, second distribution, and we're going to number 4, inverse t. The area we're going to be putting in is 0.975 because we're finding the area to the left of 97.5% of the curve. The DF we enter here is 15, which is 1 less than the sample size 16, and we paste this. And we pull out a t-score of 2.131. We're going to take 3 decimal places, 2.131. So like with z-scores, we had 3 decimal places for our z-scores. We are going to use 3 decimal places for these t-scores. But every problem we do is we're going to need to go to this calculator function, inverse t, and get this t-score. It's not something that we can memorize. Okay. So now let's plug into our formula, knowing that we have an actual value for the t-score instead of that notation. So let's plug in for x bar 125. For the t, we're going to be plugging in 2.131, and s will plug in 15, and n is 16. Okay, so even though we put into our calculator 15 for degrees of freedom, that's 1 less than the sample size, the formula still asks for the actual sample size, so we're going to put in 16 here. And then we're going to evaluate this the way we would any confidence interval, like in the previous lecture. We're going to go to our calculator, plug this in, and get our lower and upper limits. So here I am. I'm going to go 125 minus 2.131 multiplied by the standard deviation of the sample divided by the square root of the sample size. This square root of the sample size we could do in our head. That nicely comes out to 4, but if you don't, you need to use your square root symbol. Okay, 117, and we're going to round to 2 decimal places here, 117.01. And on the other side, let's second enter to repeat that line. Let's back up to the minus and turn this into a plus, and this is 132.99. So if we make an arrow for our confidence interval that goes from 117.01 to 132.99, we have our point estimate in the middle at 125. To interpret this confidence interval, it's the same kind of interpretation as the previous lecture. Nothing changes here. We're still 95% confident that the true mean fasting blood glucose level of all patients at the clinic is from 117.01 to 132.99. So lots of things do not change from the previous lecture to this lecture, but some things do change, and we really want to be careful about using t-scores instead of z-scores. Other than that, things are very similar. Now let's do the margin of error on this confidence interval. Let's take 132.99 minus 117.02 and divide by 2. I get negative 7, plus or minus 7.99, which means that we could take our point estimate of 125, subtract 7.99 to get our lower limit of the confidence interval, and add 7.99 to get the upper limit of the confidence interval. This means that we could write our confidence interval in 2 ways. We can either say 117.01 to 132.99, and I mean the word 2 here, or we can write it as 125 plus or minus 7.99. Now we're going to repeat this with a different confidence level. We're going to increase our level of confidence, and we saw what this happened in the previous lecture. Things changed in the confidence interval that came out after we changed our level of confidence. So let's see what happens here. Recall that from the picture that I showed you before, if you block off 99% of the center, then the area that is to the left of this vertical line is 99.5%. On the calculator, that is an area of 0.995. So this is going to result in a different t-score. The calculator is going to help us get that other t-score. The formula is generally very similar, except for the new t-score that we're going to be using. So let's go to inverse t, the same as before, and we're going to put in 0.995 for that area. We're going to put in the same df as before, 1 less than your sample size. 16 is your sample size, so the df is 1 less than that, 15. Paste it, and let's see the t-score that we get this time, 2.947, which is a bigger t-score because this vertical line is further out to the right than it was when we blocked off the middle 95%. So the t-score is getting pushed further to the right. So the bigger t-score, when we plug that into the formula, is going to widen the confidence interval. So let's plug that t-score in along with the other numbers. 125 here, 15 here, and 16 for the square root of n. Okay, and putting in that new t-score is going to widen this confidence interval. So take a minute, pause, and put this in your calculator and ensure that you can also get the same answer, 113.95 to 136.05. Okay, visualizing this using an arrow, on the low end, we have 113.95, and the high end, 136.05, and the point estimate in the center is our sample mean, 125. We are 99% confident that the true mean fasting blood glucose level of all patients at the clinic is from 113.95 to 136.05. Okay. The margin of error for this second version with the 99% confidence interval is 113.95. Oops, this should actually be written the other way. We have to subtract, let's change that, 136.05 minus 113.95, sorry. Okay, we're going to do the subtraction that way and divide by 2, and it's 11.05. And when we visualize that from our point estimate, negative 11.05 on the left brings you to 113.05. And from the point estimate, adding 11.05 brings you to 136.05. Okay, so that's how we do problems involving the t-distribution. I have another problem I'm going to do from beginning to end, very similar. So what we want to keep an eye out for in the wording of our problem is whether or not we have the population standard deviation or the sample standard deviation. A healthcare researcher wants to estimate the average systolic blood pressure of patients visiting a clinic. For a sample of 36 patients, the mean systolic blood pressure was found to be 128. So I'm going to write these things down as we're coming across them. That's the mean of the sample, X bar, 128. And the sample standard deviation is provided instead of the population standard deviation as 12, which means we're going to be using the t-distribution. A 90% confidence interval is going to block off the middle 90%, but the t-score over here has 95% of area to its left. Okay, and because of that, we're going to be putting into the calculator for inverse t, we're going to be using 0.95. Construct and interpret a 90% confidence interval to estimate the true mean systolic blood pressure of all patients visiting the clinic. Find the margin of error for the confidence interval. So here's that picture again. 95% of area is to the left of this vertical line. That's the value of the t-score we're going to be using in the formula. So go to the inverse t and plug in 0.95, 35 because the sample size is 36, so your DF is 1 less than that, 35, and paste, and you get a t-score of 1.69 or 1.690. Okay, so we have our all the numbers that we're going to be using in our formula. We have an S and not a sigma, so we're going to use S divided by the square root of n instead of sigma divided by the square root of n. The t-score we're going to replace with 1.690. So plugging in those numbers, we have 128 minus 1.690 times 12 divided by the square root of n, the square root of 36, 128 plus 1.690 times 12 divided by the square root of 36. And there's the answer. I'm going to show you how to get it on the calculator. Okay, so let's take 128 minus the t-score, 1.69. You can leave off the last 0, times 12 divided by the square root of 36. 124.62, and let's repeat that, changing the minus to a plus. 131.38. So putting this in a visual, the arrow here we have in the center 128. We have the low end of the confidence interval and the high end of the confidence interval. And to interpret it, we say we are 90% confident that the true mean systolic blood pressure for all patients visiting the clinic is from 124.62 to 131.38. So the margin of error, we're going to take 131.38 minus 124.62 and divide by 2, and it turns out that's 3.38. Do this 131.38 minus 124.62 divide by 2, 3.38. Okay, so that means we can subtract this margin of error from 128 to get 124.62. We can add a margin of error to 128 to get 131.38. Okay, let's compare. We're going to do a problem where we compare two different, we're going to look at patients with diabetes and without diabetes and do a blood glucose level comparison. So this problem is a little different than the previous problems involving confidence intervals because instead of providing you with a sample mean, this problem gives you raw data and you have to figure out the sample mean. So let's read the scenario. A physician wants to develop criteria for identifying atypical fasting blood glucose levels and determine whether there are significant differences between patients with and without diabetes. Use the sample fasting blood glucose levels measured below. So we have a sample of size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 patients with diabetes, we have their fasting blood glucose levels, and without diabetes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have their fasting blood glucose levels. The question says find a 95% confidence interval for the patients with diabetes. Find a 95% confidence interval for patients without diabetes. And we're going to use the results and compare and decide if it's possible that the population mean fasting blood glucose level for patients with and without diabetes is the same. So notice that besides the raw data, there are no other numbers provided to you beyond the level of confidence. So all the information that you need is in the raw data. So we don't have a provided sample mean or a sample standard deviation. In order to do this problem, we have to calculate the sample means and the two sample standard deviations with one var stats. So we are going to go to the calculator. We're going to put each one into its own list. I'll use L1 and L2. And we're going to run one var stats on each list to find the mean and standard deviation. Okay, and I'll take you through this on my calculator. So we're going to press Stat and then Edit, and this is from a previous lecture. Let me clear this out from L1 and from L2. So I'm going to put the data for patients with diabetes in L1. 135, 120, 150, 140, 145, 155, 130, 125, 160, and 138. And without diabetes, 95, 88, 92, 105, 99. Oops, something's going wrong here. After 88, sorry, 92, 105, 99, 90, 85, 100, 102, 98. Okay, so let's do patients with diabetes first. Quit this screen. Stat, Calc, 1var stats, L1, where are data with diabetes, and enter. The mean of that group of numbers is 139.8. And since that data represents a sample, we have access to the sample standard deviation. It would be incorrect to use population standard deviation because that data represents a sample. So we are using SX. It would be 12.9254, round to round to 4 decimal places. So take out the mean and standard deviation for the sample. And we're going to do this again with the patients without diabetes in L2. And we get 95.4 as the mean. And again, it's a sample. So the sample standard deviation, 6.5013. Now, keep those numbers handy. We're going to be using them in our formula. Okay, so here are the numbers that we got from our calculator. And we're going to be plugging them in the formula in the same way we did the previous problem. Now we're going to create two confidence intervals, one for patients with diabetes, one with patients for patients without diabetes. Both confidence levels, let me go back a slide. Both confidence levels are going to be 95. So the levels are going to be equal. Okay. So for a 95% confidence interval, when you block off the middle 95%, the area to the left of this vertical line is 97.5%, which as a decimal is 0.975. And we use this in inverse t to figure out what that actual t-score is, so it could be plugged into the formula. So we go to inverse t on the calculator. Let's do that first. 0.975 is your area to the left, and since the size of the sample is 10, you are using a DF of 9. So we have 2.262 as the t-score. This is the t-score we'll be plugging in here and here. The rest of the numbers are all coming from what we got when we ran 1var stats. 139.8 for the mean, sample standard deviation 12.9254, and sample size is 10. So let's plug all that into the formula. 139.8 minus 2.262 for the t-score, standard deviation 12.9254, and divided by the square root of n. We do that on the left and we do it on the right, minus and plus, and we get an answer. Let me show you on the, so plugging this in, 139.8 minus 2.6 262 times 12.9254 divided by the square root of the sample size 10. And then repeat this on the other side with a plus instead of a minus. 130.55 to 149.05. Okay, so there's our confidence interval. And to interpret this confidence interval, we are 95% confident that the true mean fasting blood glucose level for patients with diabetes is from 130.55 to 149.05. Okay, so I'm not going to do the margin of error. You're very familiar with how to do that at this point. So I'm going to jump right into the second part of this comparison, which is the confidence interval for patients without diabetes. So we already calculated the mean and standard deviation using the raw data, and we're going to plug that into the formula. So that's a different mean and a different standard deviation. The same t-score though, because the sample size is the same. It's still size 10 and the confidence level is the same, still 95% level of confidence. So the t-score stays. So plugging the other numbers in, we're only changing here the mean and the standard deviation. Otherwise, it's the same as before. And this time we get a number, we get 90.75 to 100.05. To interpret this confidence interval is the same kind of interpretation, same level of confidence. We are 95% confident that the true mean fasting blood glucose level for patients now without diabetes is from 90.75 to 100.05. So the important part of the question that follows is it possible for both patients with and without diabetes to have the same population mean? The same population mean, the same mean that we're attempting to estimate here. Well, the way we can figure that out is by examining where the two confidence intervals lie with respect to one another. So remember, I got the confidence interval for patients with diabetes is this blue arrow from 130.55 to 149.5, and the patients without diabetes is this magenta pink arrow from 90.75 to 100.5. If I look at them together, the numbers do not overlap. You see where 100.05 is the high limit of patients without diabetes, and 130.55 is the lower limit for patients with diabetes. And there's this big gap between those two confidence intervals. There's no overlap. Now, the purpose of a confidence interval is to always estimate if mu, or estimate where mu is, that mu is somewhere in that confidence interval. Now, if we're trying to estimate the population mean blood glucose levels or fasting blood glucose levels for patients with and without diabetes, and mu is estimated to be in this pink range for without diabetes, and mu is estimated to be in this blue range for people with diabetes, then there's the chance that they are the same is not likely. Given what we're looking at right here, there is this big gap between the two confidence intervals, and the population means cannot be the same. Okay. The confidence intervals do not overlap, providing evidence that the population mean, this is not supposed to say that. Hold on, let me fix this. Okay, so the confidence intervals do not overlap, See, there's a gap between them, providing evidence that the population mean fasting blood glucose levels for patients with and without diabetes are likely different. Now, are we 100% certain that they are different? No. We have 95% confidence that the population mean fasting blood glucose levels for diabetics is greater than that for non-diabetics. We're 95% confident of this, but there's always a chance that a sample mean, you could get a sample mean where they both do overlap. It's not going to be very likely, but so in this case, we say we're 95% confident that the blood glucose level for patients with diabetes are higher than for patients without diabetes. So there is a homework question like this, and because the numbers are randomly generated, we don't know ahead of time if you're going to end up with two confidence intervals that overlap or do not overlap. If they don't overlap, like in this case, then we're going to say that the two population means are likely different. If they don't overlap, I'm sorry, if they do overlap, if they were to look like this instead, then it is possible that there is a same population mean for both of those groups. Okay, and that's how you would interpret this type of question. So that's the confidence interval lecture. We've done two of them now, and you have two homework assignments on them. A lot of times students mix up the type of confidence interval problem, and they apply one approach to the wrong confidence interval. So you want to be really careful about reading the problem and ensuring that if you have sigma, you're going to be using the normal distribution with z-scores. If you have the sample standard deviation S, you're going to be using the t distribution with t-scores from the inverse t function on your calculator. So I hope this helps. Ask me if you have any questions, and I'll see you at the next lecture.